When we solve the auxiliary equation, we get repeated roots. We only find one solution initially, which is written as y1 is equal to e power mx. Now, this is the quadratic equation because the power is 2. So we need to find the second solution as well. For that, we'll be using a method called reduction of order. The formula to find the second solution is this. Here, y1 is the first known solution, which is e power mx, and p of x is the coefficient of y prime in the standard form of the equation. Suppose we have a differential equation with the constant coefficients. So first, we convert it into the standard form by making the coefficient of the y double prime equal to 0. Hence, we are going to be dividing the either side of the equation with a. This will be giving us this equation. Now, we already know that the p of x here is the coefficient of y prime, this in the standard form. So the value of p of x is going to be equal to this. Now, substituting the values into this original equation we've got here. So we know that y1 is equal to e power m1x. Let's substitute it here. Now, expanding the bracket here, we are going to get 2m1x, so let's simplify it. To find the value of this 2m1, we'll be using the quadratic equation and find the solution of m. For the case where the roots are real and distinct, we know that b squared minus 4ac is equal to 0. So this entire term becomes 0, leaving us with minus b divided by 2a. You can see here we are having 2m1 here. So we'll be taking the 2 to the other side of the equation. This will be giving us now we are going to be substituting minus b divided by a here and solve this equation. So substituting minus b divided by a at the place of 2m1, we get this. Now, since we are doing its integration with respect to x, we're going to take this out of the integral sign and rewrite it. We know that the integration of a constant is equal to x. So instead of writing this, you'll be just writing x. Now, you can see that the numerator and the denominator are exactly the same. So they're going to cancel out each other, leaving behind e power m1x the integration of 1 is going to be x. So the second solution is going to be e power m1x times x. Thus, at the end of the day, we are getting the general solution of the second case that is equal to e power m1x plus substituting this here, which is going to be e m1x times x with a constant c1 and c2. Now let's see how we can derive the general solution of the third case. In third case, we had discussed that the roots we are going to get are complex. So it is going to be m1 is equal to alpha plus iota beta, and m2 is going to be equal to alpha minus iota beta. Now we are going to be substituting this into the general solution, c1 e power m1x plus c2 e power m2x. Substituting m1 and m2 into their respective positions, we get now expanding the exponent brackets, we are going to rewrite this and take e power alpha x common because it is going to be common in both of them. So let's do that. Now we are going to take e power alpha x common. Let's do that directly. Now we are going to be using the Euler's identity to expand these exponents. The Euler's identity states e power iota theta is equal to cos of theta plus iota sine of theta. Instead of theta, we'll be writing beta x. So e power iota beta x is equal to cos beta x plus iota sine beta x. Now let's substitute that here. And for the e power minus iota beta x, we're just going to be changing the sign from positive to negative. Now we are going to be expanding the brackets C1 and for C2. And we are going to be collecting cos terms together and the sine terms together. So let's do that. Now we are going to assume that C1 plus C2 is equal to A, and iota C1 minus C2 is equal to B. So let's substitute A here, and here we're directly going to be substituting B. This will be giving us our general solution for the third case.